Good afternoon, ladies and gentlemen, distinguished guests, dear colleagues and friends. On behalf of organizers, it is my great pleasure and honor to welcome you to the 10th International Conference on Mathematics and Informational Technologies Research and Education, an event that marks the opening of the Mathematical Week in Chisinau, which is dedicated to the centenary of academician Valentin Belousov. Thank you all for accepting our invitation and joining us here today, contributing to the success of this special edition of the conference. And we especially thank our distinguished guests for accepting our invitation to attend the opening ceremony. And please welcome Professor Igor Sharov, Rector of Moldova State University. Associate Professor, PhD in Mathematics, Galina Rusu, Secretary General of the Ministry of Education and Research of Republic of Moldova, and academician Svetlana Kozhokarov, Vice President of the Academy of Science of Moldova. And let us begin with the welcome address of Professor Igor Sharov, Rector of Moldova State University. Please, the floor.
Vă mulțumesc, stimată doamnă secretar general al Ministerului Educației și Cercetării, stimată doamnă vicepreședinte Academiei Republicii Moldova, stimată doamnă decan, onorată asistență, dragi prieteni, dragi participanți la conferința ajunsă la acea de 10-a ediție. A 10-a ediție vorbește deja despre o sustenabilitate. A 10-a ediție vorbește că este unul din evenimentele centrale care unește cercetătorii din 9 țări la această ediție și vreau să profit de această ocazie și să doresc succes în realizarea obiectivelor care le-ați propus. Credeți-mă, vă rog, că grupul de organizare în frunte cu doamna decan a depus foarte mult suflet pentru organizarea acestui eveniment și vreau cu această cale să le mulțumesc. Să le mulțumesc partenerilor noștri care ne-au ajutat în organizare, care din modestie nu au dorit decât să vină cu un mesaj de salut și această inițiativă a lor. Imaginează și emoțiile pe care le trăiește doamna secretar general Galina Rusu, fiindcă acum 2 ani, în calitate de decan a facultății, organiza acest eveniment, ori doamna vicepreședinte Academiei, exact împreună cu dumneavoastră ca și matematicieni, sunteți în albia dumneavoastră. Vă doresc mult succes și mulți ani înainte pentru MITRE. Mulțumesc mult!
Thank you, Professor Sharov, for your inspiring words. And now it is my pleasure to welcome Galina Rusu, Secretary General of the Ministry of Education and Research of the Republic of Moldova, to greet our participants, please.
Yeah, thank you so much. I believe that I can be heard. I wanted to greet you staying since I want to express all my gratitude to our participants. Yes, I am sure that we, being as teachers, we have yes, a good, no, not only good ear, but also a voice to be heard. Thank you, dear rector, dear chair, dear vice chair of the MITRE conference. It's indeed a great pleasure to participate at the MITRE conference together with you, with all our participants, and to be here, since I feel the MITRE conference like the path that I have in the research area, since I was part of this conference as a participant in some sections, starting maybe with 2006, then trying to help to organize the conference and all the activities when Mr. Andrei Berjan, the dean of the faculty at that time, was the chair of the conference, then organizing the conference as dean of the faculty and now as invitee. It's indeed that I feel that it is my family, and this conference expresses also the development of the research in the domain of mathematics, computer science, and also in the didactic of mathematics and the computer science in our country. It was initiated by a group of very dedicated mathematicians and specialists in informatics and in didactics, very dedicated with very low resources, at the beginning without resources, and it is now at the anniversary. It is now at the 10th anniversary. It is indeed a great success of the organizers, a great success of our community of mathematicians and informaticians, let me say, of our country. Let me express my gratitude for all participants, for our invitees from 9 countries. It's a great success of this team. I was looking at the program, having so interesting communications, valuable communications. Thank you all for your contribution. Thank you all for being part of our event, this event, and this year it is so nice to see that we have the MITRE conference, then we have the mathematical school for our young people, and then we have the Belousov conference, having all the community contributing to the development of the quasi-group areas, but let me say that we do not speak about one only direction. We speak about mathematics itself and its development. Thank you all, and use this time to communicate, to create, as it is. It was in the previous events, previous conference, and let's keep that we have the connections that we have. Let's try to connect the young people to this community, and to prove that mathematics is indeed can indeed have a very valuable contribution on the development of different sectors and the development of our country. And the researchers are a community that can change the direction of our country, and can improve the country in the way that we want to see it. Thank you all very much.
Thank you, Professor Belousov, for this thoughtful address. And now, please welcome academician Svetlana Kozhakaro, Vice President of the... Sorry, let me present you. Vice President of the Academy of Science of Republic of Moldova, to deliver her speech, please.
Thank you. Stimate domnule rector, domn profesor Igor Sharov, stimată doamnă secretar general de stat al Ministerului Educației și Cercetării, doctor conferențiar Galina Rusu, stimată doamnă decan, doctor conferențiar Niculiță, dear colleagues, dear guests, ladies and gentlemen. On behalf of the Academy of Sciences of Moldova, I am honored and delighted to welcome you at the opening of Mathematics Week, a significant academic event hosted by Moldova State University, bringing together three major scientific gatherings: the International Conference, we used to name it shortly MITRE, the summer school for young researchers in the field of Quasigroups, and the corresponding conference of Quasigroups and related systems. These events hold a special significance as it is dedicated to the 100th anniversary of Professor Valentin Belousov, a distinguished mathematician and the founder of the Moldovan School of Quasigroups theory. His contribution have not only shaped the landscape of algebraic structure in Moldova, but also inspired research far beyond our borders. His legacy continues to live throughout generations of mathematicians who built their career upon his foundational work. The Academy of Sciences of Moldova has consistently regarded mathematics as a cornerstone of fundamental science, a pillar of logical thinking, and a vital component in the advancement of technology, education, and society as a whole. I would like to take this opportunity to inform you that the competition for the Academy of Sciences prizes, one of which is in the field of mathematics and computer science and is named after academician Vladimir Andronakevich, will be announced shortly, and I invite and encourage you to apply. We are proud to witness the participation of scholars from Moldova, Romania, Ukraine, Canada, the Czech Republic, Brazil, Spain, and many other countries, reflecting the international prestige and collaborative spirit of this scientific community. Your presence enriches the intellectual climate and contributes to fortifying bridges of knowledge and friendship across borders. To the organizers, we express our deep appreciation of their dedication and effort in making this week possible. To the young researcher, we extend our encouragement. May this experience spark your curiosity, refine your skills, and connect you to mentors and colleagues who will shape your academic journey. Events like this are not only opportunities to exchange ideas and showcase results, but also moments of reflection, cooperation, and inspiration for the future. Let this week be a tribute to the power of mathematics, to the memory of a great scientist, Professor Valentin Belousov, and to the vibrant global community of researchers that keeps pushing the boundaries of knowledge. I wish you all a fruitful, stimulating, and memorable mathematical week.
Thank you, academician, for these insightful, encouraging words. And I would like to express, I think, on behalf of our entire community, I would like to express our thanks and our gratitude for the sponsor who make possible to organize this conference, and the events will follow this conference. So thank you very much to the company MTSting in Premier Energy. Thank you very much. I think we need to applaud them, because without them it will be very, very difficult to organize such events. Thank you very much. We thank our distinguished guest for officially opening our event, which marks the beginning of the Mathematical Week, and honors academician Belousov. And I would like to wish all you and all our conference very success. And before we starting to work, hard work is before us, I would like to invite you to make a family photo, and after that, to have a very short, I'm joking, coffee break. So please let us go outside before the stairs and first make the family photo. Thank you very much. Thank you all.
speaker, Dr. Andrei Alexandru, Secretary of State and President of National Authority for Scientific Research in Romania. Dr. Alexandru is a distinguished informatician whose career bridges high-level research and national science policy. He holds a PhD in informatics and serves as a senior researcher at the Institute of Theoretical Computer Science of the Romanian Academy. A graduate of the Faculty of Mathematics at Alexandru Ioan Cuza University in Iași, he completed his studies at the top of his class with a perfect mark of 10. Dr. Alexandru's research lies at the intersection of computer science and mathematical logic. He has published extensively in leading international journals and is the author of 2 monographs with Springer. Beyond academia, he has played a pivotal role in shaping Romania's research and innovation ecosystem, leading national strategies, advancing legislative reform, and overseeing major European funding programs. He is widely recognized for his rare ability to connect rigorous theoretical insight with forward-thinking, impactful policy. Dear colleagues, please join me only welcoming Dr. Andrei Alexandru, who will deliver the conference's first plenary lecture on the topic, Atomic Cardinalities. Dr. Alexandru, the floor is yours.
First of all, ladies and gentlemen, distinguished researchers, distinguished guests, thank you for inviting me at this very important conference. I would present a paper regarding atomic cardinalities, whose goal is to provide a framework for managing infinite structures in terms of finite. More exactly, we try to provide a mathematical tool for modeling the infinite in a discrete manner. So, my presentation, Atomic Cardinalities, starts with an introduction and a section of original results. First of all, we will describe an original theory of me and my co-worker, Professor Gabriel Ciobanu from Iași, related to finitely supported structures. We start with an intuitive motivation regarding mathematics and reality. And it is amazing that what we predict from the manipulation of symbols in mathematics is actually realized in the real world. Mathematics enabled extraordinary prediction about several aspects of the material world, from the very small, such as Higgs bosons, to the very large, such as gravitational waves. And it seems that the power of physics lies in the use of mathematics. It produces not only models of reality, but reveals reality itself. Bernard Russell, in his book, An Outline of Philosophy from 1927, says, physics is mathematical not because we know so much about the world, but because we know so little. It is only its mathematical properties that we can discover. The relationship between mathematics and reality. Mathematics does not merely offer the most effective ways of modeling the universe, but it is a faithful portrait of what the universe really is. And Tegmark, in his 2040 book, Our Mathematical Universe, My Quest for the Ultimate Nature of Reality, introduces what he calls the mathematical universe hypothesis that denies that anything exists other than mathematical objects. And various questions naturally appear. For example, what are the numbers in the physical world, in the material world? Well, the real numbers are used in almost all the physical theories. However, the numbers used in physics is a subset of the rational numbers because the outcomes of the measurements have finite decimal representations. Regarding experimental sciences, well, looking to the advancement of science, for example, in astronomy and in other experimental sciences, knowledge is based on a finite number of material things and a finite number of observations. The properties of these finite material things are then extended to an infinite space, a space which is the mathematical universe working with infinite sets. In fact, we actually extend the finite knowledge to an infinite universe just to align it with the general approach in current mathematics, which is represented by the Zermelo-Frankel standard set theory. And the main question naturally appeared: is it possible to describe the knowledge process in a better mathematics, extending but not denying the Zermelo-Frankel approach? And in mathematics, we already have some set theories with atoms. For example, Zermelo's original axiomatization of set theory from 1908, the Zermelo-Frankel set theory with atoms, allows objects that are called atoms that do not have an internal structure. That means they may be members of sets, but are not made up of other elements. That means they are similar to the empty set. However, they are infinitely many, and they can be compared only for equality. They do not have an internal structure. Philosophers use this material set theory to reason about the ontology of the real world. Atoms are supposed to be actually the existing material things, the things that exist. Thus, the Zermelo-Frankel set theory with atoms is the general framework we intend to extend with a single axiom, saying that we work actually with finitely supported sets. This expresses that we work effectively with finite sets, even we accept infinite sets. So, to motivate this approach, we start from the Banach-Tarski paradox. Banach and Tarski informally realized that you can turn one sphere into two by partitioning the uncountable infinite set of points it contains into an uncountable infinite number of countably infinite sets. The mathematical proof of these results from 1924 depends crucially on the axiom of choice in the Zermelo-Frankel set theory, which allows the construction of non-measurable sets. That means the construction of collection of points that do not have a volume in the ordinary sense, and whose construction requires an uncountable number of choices. Formally, the Banach and Tarski theorem is presented in the following slide. This is the theorem given a solid ball in the three-dimensional space. There exists a decomposition of the ball into a finite number of disjoint subsets, which can then be put together, reassembled, in order to obtain two solid spheres, each one identical with the original ball. So, from one ball, you can make two balls identical with the original one. Furthermore, the reassemble process involves only moving the pieces around and rotating them without changing their shape. And the reconstruction can work with as few as 5 pieces. This was proved by Terence Tao in 2011. This is a nonsense if we look to the geometrical intuition. So from one sphere, we can construct two without changing the shapes of the divisions, just translating and rotating them. So, naturally, if we get a theory in which the axiom of choice is not valid, then we hope to obtain a more realistic mathematics. However, we try to construct a theory without denying the independence of the axiom of choice in the non-atomic framework, as we will prove below. So we will do not weaken the classical Zermelo-Frenkel framework, but we will extend it to the atomic case, and we eliminate such paradoxes. So in the following, we present such a candidate to a more realistic mathematics obtained by extended Zermelo-Frenkel with atom set theory with a single axiom, saying that we work with finitely supported sets. Regarding the axiom of choice, it has an interesting history. In 1922, Frenkel introduced the permutation models of set theory with atoms in order to prove that the axiom of choice is independent from the other axioms of the classical set theory. This permutation model was generalized by Lindenbaum and Mostovsky in 1938. Furthermore, in 1948, Gödel also proved the independence of the axiom, the consistency of the axiom of choice from the other axioms of the Zermelo-Frenkel set theory. What means the consistency? Means that the negation of the axiom of choice is not a theorem in the Zermelo-Frenkel framework. Or equivalently, there exist models of Zermelo-Frenkel with choice. Finally, in 1963, Cohen proved the full independence of the axiom of choice. That means it proved the consistency of the axiom of choice and of the negation of the axiom of choice, meaning that there exist models of Zermelo-Frenkel with choice set theory, and also there exist models of Zermelo-Frenkel without choice set theory. For proving this, Cohen used the so-called forcing method, which is derived from the Frenkel and Mostovsky original permutation method. Well, finitely supported sets have historical roots in the permutation model of set theory with atoms. A permutation model is, as I said, a model of the Zermelo-Frenkel with atom set theory constructed by using a group of permutation of atoms. And furthermore, finitely supported sets can also be described in the classical Zermelo-Frenkel set theory by equipping classical sets with actions, with group actions of the group of all one-to-one and onto finite transformations of the universe of discourse onto itself. And we impose, as we will see in the following slides, a finite support requirement. Here we have the formal definitions. What is an invariant set? Is actually an usual Zermelo-Frenkel set X equipped with a group action dot of the group of all finite permutations, that are permutations permuting only finitely many elements, of a certain fixed infinite Zermelo-Frenkel set A of basic elements for the construction of our universe, that are atoms, having the additional property that any element X of X is finitely supported. In a pair X and dot formed by a Zermelo-Frenkel set X and a group action dot of the group of all finite permutation of A, an element X is finitely supported if there exists a finite set of atoms S such that any permutation P that fixes S point by point, pointwise, also leaves X invariant under the group action. We have here in the third item the definition of the support. The support of an element is the least finite set supporting the element. Or equivalently, it is the intersection of all finite sets supporting the related element. An empty supported element, that is an element supported by the empty set, is called equivariant. Whenever we have a group action on X, we can canonically describe a group action on the power set of X. So we keep the power set of X with the action star defined by P star Y is actually the set obtained by applying P to each member of I. So we consider the set finitely supported power set of X formed by all the finitely supported elements in the power set of X with respect to this SA action. That means a finitely supported set is actually a finitely supported element in the power set of X. Finally, we have the definition of uniformly supported sets. A subset of an invariant set having the property that all its elements are supported by the same set of atoms is called uniformly supported. That means in a uniformly supported set, all the elements are actually supported by the same set of atoms. Here we have examples of higher order group actions. For example, if we have two invariant set X, Y, their Cartesian product is also an invariant set. A relationship between a binary relation between two invariant sets is finitely supported if it is finitely supported as a subset of the Cartesian product of the two invariant sets, and particularly functions that are particular relations have an interesting property. A function between two FSM sets, two finitely supported sets that are abbreviated as FSM sets, X and Y, is supported by a finite set S if and only if F commutes with the action. That means Fp.x is P applied to Fx in the second set for all X of X. And we have a notation for the set of all finitely supported functions from X to Y. Now, we were able to prove, and the proof is not simple, it's quite complicated, that the following sets that are obviously infinite and are of exponential type satisfy a form of finiteness. That means they do not contain infinite uniformly supported subsets. So we consider X a general finitely supported set having at least two elements, and X does not contain an infinite uniformly supported subset, and Y is a finitely supported set having at least two elements, such that the finitely supported power set of Y does not contain an infinite uniformly supported subset. And the following huge finitely supported sets are somehow finite. For example, NA, that is the disjoint union of A with A with A, n times. The Cartesian product of A with A with A, n times. The finite power set of AN, the finite power set of NA, the finitely supported power set of AN, the finitely supported power set of NA, the finite power set of the finitely supported power set of AN, the finite power set of the finitely supported power set of NA, the exponential spaces AAN or ANA. That means the set of all functions from AN to A, and the set of all finitely supported functions from NA to A. The finitely supported power set of the N power set of A. N power set of A means the set of all subsets of A of size n. And the other higher sets, more generally, we are able to prove that the set of all finitely supported functions from AN to X and the set of all finitely supported functions from NA to X and the finite power set of X, all of them do not contain uniformly supported subsets, so they are somehow finite, as we will prove below, as I will prove in the following slides. Well, the applications of finitely supported sets naturally appeared in the last years in computer science. Starting from 2000s, the finitely supported sets have become of great importance from the foundations of computer science, since they support new ways to represent the syntax of formal systems involving variable binding operations. Inductively defined finitely supported sets involving the name abstraction together with Cartesian product and disjoint union can encode syntax modulo renaming of bound variables. In this way, the standard theory of algebraic data types can be extended to include signatures involving binding operators. There is an associated notion of structural recursion for defining syntax manipulation functions and a notion of proof by structural induction. Finitely supported sets were also used to study automata and Turing machines over infinite alphabets. Furthermore, they are logical notions in Tarski's sense, and invariance under permutation reflects the logicality, the logical notions, as Tarski's claimed in 1986, his celebrated paper, What Are Logical Notions?, which is published in the History and Philosophy of Logic. The idea of this invariance is that the invariance under groups of permutations can be used as a measure of generality, and that invariance under the group of all permutations correspond to the utmost generality. What does this mean? This means that a notion is logical if it is unchanged under all the one-to-one and onto transformations of the universe of discourse onto itself. And we are able to prove that these finitely supported sets satisfy the form of logicality of Tarski. This invariance under permutation has historical roots in the Erlangen program of Felix Klein for the classification of various geometries according to invariance under suitable groups of transformations. Well, what are finitely supported structures? And this is an original approach. A finitely supported structure is actually a finitely supported set equipped with a finitely supported internal law. The general theory of finitely supported structures has a general name of finitely supported mathematics. And finitely supported mathematics actually represents the reformulation of the Zermelo-Frenkel classical algebra obtained by replacing non-atomic set structure to atomic but finitely supported set structure. As I said above, the theory of finitely supported structures allows a discrete representations of possibly infinite structures that contain enough symmetries in order to be consciously handled. More exactly, this theory allows us to treat as equivalent the objects that have a certain degree of similarity and to focus only on those objects which are really different and they are represented by the support of the structure. Well, the framework of the finitely supported structures contain two parts. The Zermelo-Frenkel part, which is actually the non-atomic part of the finitely supported structures, and the atomic part. Our goal is to analyze whether a classical Zermelo-Frenkel result remains valid when we replace non-atomic structure with atomic but finitely supported structure. And we have to be internally consistent, meaning that when proving such a result, we have to check that every construction is finitely supported, even in the intermediate steps. Here, we prove that we do not have a simple task. For example, there are results that hold in the Zermelo-Frankel framework, but do not hold, do not remain valid in the new atomic framework. For example, we know two results. Multiple choice principle and Kurepas maximal anti-chain principle are both equivalent with the axiom of choice in the classical Zermelo-Frankel set theory. However, Jack proved that multiple choice principle is valid in the second Frankel model, while Kurepas anti-chain principle is valid in the first Frankel model. Furthermore, the axiom of choice does not hold in these models. So, the following results: Kurepas principle implies axiom of choice, and multiple choice principle implies axiom of choice, which are valid in the Zermelo-Frankel framework, fail to be valid in the new atomic framework. So, we have to introduce meta-theoretical approaches to prove that a structure remains finitely supported when it is, I don't know, it goes to a higher level. So, a proof of an FSM result should be internally consistent, as I said above, in the finitely supported mathematics and not retrieved from the Zermelo-Frankel framework, meaning that it should involve only finitely supported structures, even at the intermediate steps. And we have two meta-theoretical methods to prove this. The first one is an hierarchically constructive method for supports, and the second one is given by a refinement of the meta-theoretical equivalence or finite support principle, which is derived from the theory of nominal sets of Pitts and Gavai, allowing to prove boundedness properties for supports. It actually reduces to the first method being a step-by-step construction of supports. In the following slides, we will have a photo of these methods, the constructive method. These methods represent an hierarchically, step-by-step construction of the support of a certain structure by employing the supports of the substructures of the related structure. The meta-theoretical S-finite support principle claims that for any finite set S of atoms, anything that is definable in the higher order logic from S-supported structures using S-supported constructions is also S-supported. Here we have the bibliography for this theory of finitely supported structures. The first book, published by Springer, Foundation of Finitely Supported Structures, a set theoretical viewpoint. And the second one, also at Springer, Finitely Supported Mathematics. There are two monographs that describe the framework of finitely supported structures. We are now able to present very short some original results in this presentation, specifically in this presentation. What are the cardinalities? So we introduce and study the notion of cardinality, and we define specific finitely supported order relations on cardinalities, where the cardinalities are ordered via finitely supported injective functions or, respectively, via finitely supported surjective functions. We are also able to present several arithmetic properties of cardinalities. We are able to prove that in the new framework, the Cantor-Schroeder-Bernstein and the Cantor theorem are preserved, while the dual of the Cantor-Schroeder-Bernstein theorem is no longer preserved. First of all, we analyze what happens with the choice principles, the axiom of choice, and stronger forms such as generalized continuum hypothesis, or weaker forms such as the other choice principles in the atomic framework. None of them is valid. The axiom of choice, the Hausdorff principle, Zohr lemma, principle of dependent choice, principle of countable choice, principle of partial countable choice, the axiom of choice for finite sets, the principle of Dedekind finiteness, prime ideal theorem, ultrafilter theorem, or the total ordering principle, the principle of existence of right inverses for surjective mappings, generalized continuum hypotheses are all invalid in the atomic framework. However, they still remain consistent. This is very nice because the mathematical analysis still hold in this framework. Nothing is contradicted. So they still remain consistent in the non-atomic framework, meaning that no non-atomic result is weakened under the new approach. And we introduce the notion of cardinality. Since the axiom of choice is not valid, we can no longer define the cardinality as being as the least ordinal. This happens only in the Zermelo-Frankel choice framework. So, we introduce the equivalence relation, meaning that two finitely supported sets X and Y are called equivalent if there exists a finitely supported bijection between them. This equivalence relation is an equivalent equivalence relation on the family of all finitely supported sets. And you introduce the cardinality, which is defined as the equivalence class of all finitely supported sets equivalent to X, denoted by card X, meaning that card X is actually the set of all finitely supported sets that are in bijection with X. This means that for two finitely supported sets, X and Y, we have card X equal card Y if and only if there is a finitely supported bijection between X and Y. We are now able to introduce two-order relations. We call rho 1 and rho 2. And we say card X rho 1 card Y if and only if there exists a finitely supported injective function from X to Y, and rho 2 card X rho 2 card Y if and only if there is a finitely supported surjection from Y onto X. And the major theorem says the following. The finitely supported relation rho 1 is finitely supported, reflexive, antisymmetric, and transitive, meaning that the Cantor-Bernstein theorem holds. However, this relation is not total, despite the Zermelo-Frankel with choice approach, where this relation is total. Furthermore, the binary relation rho 2 is finitely supported, reflexive, and transitive. However, it is not antisymmetric, neither total. That means the dual of the Cantor-Bernstein theorem does not hold in this approach. And the generalization of the classical Cantor theorem says that for any finitely supported set X, we have that X is in a relation rho 1 with the finitely supported power set at X, and X is different from the finitely supported power set at X, meaning that there does not exist a largest atomic cardinality. Now we have operations. Operations that are similar with the operations in the Zermelo-Frankel framework. The sum of cardinals is defined as the cardinal of the disjoint union of sets. The product of cardinals is defined as the cardinal of the Cartesian product. And the exponent of cardinals, card X exponent card Y, is defined as the cardinal of the function spaces of all finitely supported functions from Y to X. We are able to prove in the new framework that the above definitions are correct, meaning that they do not depend on the chosen representative for equivalence classes modulo the equivalence relation. Now we have properties that are similar with those in the Zermelo-Frankel framework. We have an exponent property, card Z, exponent card X dot card Y is card Z card X all applied at the exponent card Y. Card Z at the exponent card X plus card Y is card Z at the exponent card X dot card Z at the exponent card Y. The cardinal of the power set of X is actually 2 exponent card of X. And finally we have card X point multiplied by card Y all applied to card Z is card X applied at the exponent card Z multiplied with card Y at the exponent card Z. Now we are able to define some formal finiteness. that are not equivalent, they are not equivalent. So we say that x is one finite if the cardinality of the Cartesian product between x and x is different from the cardinality of x. X is called two finite if the cardinal of the disjoint union of x plus x is different from the cardinality of x. And finally, x is free finite if every finitely supported injective function from x to x is also surjective, meaning that equivalently there is no finitely supported injective function from the set of all natural numbers to x. This is also called Dedekind finiteness. Between these forms of finite, we are able to prove some relationships. This is the last slide, so I will 1 minute, I will finish this. So if x is a finitely supported set, we are able to prove the following. The finitely supported power set of x is free finite. This implies x is free finite, implies x is two finite, implies x is one finite, and the above implications are strict. If x is free finite, then the finite power set of x, the set of all finite subsets of x, is also free finite, where the finite power set of x, as I said, is the family of all finite subsets of x. If x is free finite, then the set of all finitely supported functions from an to x, where an is the n times Cartesian product of x, and the set of all finitely supported functions from na to x, or na is the n times disjoint union of a, are all free finite. Finally, if x is free finite, the set of all finitely supported functions from Pna to x is free finite, or Pna is the set of all n-sized subsets of x, and the final result, the finitely supported power set of x is two finite, implies that the finitely supported power set of x is one finite, and the above implication is strict, meaning the reverse does not hold. Finally, in this slide, I provide that the following definitions of finiteness are independent, meaning that there exists several sets that satisfy a related definition but do not satisfy other definition of finiteness. And if x is a free finite set of cardinality greater than 2, and 10 is generally denoted to be one of the sets Ka or Ak, meaning the K times disjoint union of A, or the K times Cartesian product of A with itself, the following sets A and A, the exponent of x to the exponent t, the finite power set of x, A disjoint union with the set of natural numbers, the finitely supported power set of A disjoint union with the natural numbers, and the Cartesian product of A with the set of natural numbers satisfy these forms of infinity and affinity according to the columns in this table. So, as a conclusion, in the new framework we have not only one type of finiteness, as in the classical Zermelo-Frankelov choice framework, but many other types of finiteness. So we can compare various types of finiteness, and we are able to model the infinite structures in a finitary manner, in a computable manner. Thank you very much for your attention, and if there are questions, I don't know if we have time, but if there are questions, I am happy to respond. With the non-standard analysis? Well, as I said above, no result in the classical analysis is weakened under this approach. So the entire mathematical analysis remains valid in this framework. However, by introducing the atomic part, meaning that by considering some basic elements in the mathematics, we are able to manage to describe properly all the objects that can be constructed from these basic elements we consider. So nothing in the mathematical analysis is weak. The entire analysis works as well as until now. Non-standard, what you refer? I'm not following the terminology. I don't know exactly what you refer to. What you refer? There are a lot of analysis. A lot of types of analysis. I don't know, real, on the real, on the case of real functions, on the complex functions, on the, I don't know, analysis, the derivation theory, the analysis of the functions, final reals, and other things. As I said above, nothing in the classical mathematics, nothing in the classical mathematics is weak. This is an addition to the classical mathematics. So we add something to the classical mathematics, and we are able to say, okay, what are the things? We start. This. Anything else can be described in terms of this idea. But as I said before, nothing is very classical. So neither is the classical analysis nor mechanics.
Vorbiți. Gata. Microfonul, foarte. Dacă să vă uitați în voi să puteți microfonul. Vă rog.
Domnul și-a uitat și aia Dear colleagues, it is a distinct honor to introduce Professor Mircea Sofonia, an esteemed mathematician and full professor at the University of Perpignan via Domitia, France. Professor Sofonia earned his PhD in mathematics from the University of Bucharest and subsequently completed his habilitation at Blaise Pascal University. Over the course of an exceptional academic career, he has established himself as a leading authority in applied mathematics with pioneering contributions in variational and hemivariational inequalities, contact mechanics, and nonlinear analysis. He is the author of numerous influential monographs published by leading academic presses, and with over 4,500 citations, a clear testament to the reach and significance of his work. As former director of the LAMPS laboratory, Professor Sofonia has also shown exemplary academic leadership and is frequently organizer of high-level international scientific events. His work has significantly advanced both theoretical foundation and practical modeling techniques in the mechanics and continuous media. Please join me in warmly welcoming Professor Mitya Troyan-Sofonia, who will deliver the conference's second plenary lecture on the topic, a convergence criterion for history-dependent variational inequalities. Dear Professor, the floor is yours.
Vă mulțumesc, domnule Ungureanu, pentru această prezentare. Primele cuvinte vor fi în limba română, așa se cade. Aș dori să-mi exprim bucuria de a fi aici, pe acest pământ binecuvântat al Basarabilor, unde mă întâlnesc, unde mă găsesc pentru a doua oară. Mulțumesc organizatorilor pentru această invitație, în special domnului profesor Andrei Perjan. Bucuria de a fi aici este foarte mare și vă mulțumesc pentru căldura și ospitalitatea cu care ne primiți, astfel încât, practic, ne simțim ca acasă pe pământ românesc. Încă o dată mulțumiri și let's move to English. So the title of my lecture is Convergence Criterion for History-Dependent Variational Inequalities. Here you have the outline of my talk. And I shall start to speak about convergence results, which are frequently in analysis and mechanics. Here you have a list, a non-extensive list of some convergence results. Let us remember, for instance, the convergence with respect to the perturbation of the data. So you have a problem, you perturb the data, and the solution of the perturbed problem converges to the solution of the original problem. Now, if you are doing numerics, so you penalize the problems and you have the penalty problems, and the solution of a penalty problem converges to the solution of the original problem. Also, when we deal with discrete schemes and so on. I shall continue with some convergence results in mechanics. For instance, the convergence of the solution of the frictional problem to the solution of the frictionless problem when the coefficient of friction goes to 0. And if you have a viscoelastic problem, you vanish the viscosity parameter and you obtain as a limit the solution of elastic problem. So there are many results of convergence result. But let us try to focus on this concept. We can formulate the problem in the following abstract functional framework. So we deal in a metric space XD. Let's call P an abstract mathematical object, call it a problem, and which has a unique solution. The notion of solution comes from the context. And consider a sequence UN of elements in X. What is a convergence result? Practically, a convergence result is a result of the following form. If some condition hold, then UN goes to U, converge to U. But this convergence result do not provide sufficient conditions for the convergence UN to X. They do not describe all the sequences which have this property. So I make the distinction between a convergence result and a convergence criterion. A convergence criterion is a result which provides necessary and sufficient conditions for the convergence. A convergence criterion describes all the convergences which have this property. And then you arrive to the following question. So, given a problem P, provide a convergence criterion to the solution. That means we try to describe all the sequences which converge to the solution. Now, at this level of generality, it's very hard to give concrete results. But various results have been obtained in the case when the problem P has a special structure, for instance, a variational, a hemi-variational inequality, a fixed problem, fixed point problem, and so on. And this is the aim of my lecture. I mean, to state and prove a convergence criterion for a special class of variational inequalities, to illustrate some applications, to state and prove convergence and well-posed results, and to provide some examples arising in mechanics. So let's consider the problem. It's not the most general we can consider, but it's a good problem, large enough. It's yeah? And the problem is the following. We have a real reflexive, strictly convex Banach space, X. The notation are standard. You have here all the notations. And the problem is to find a function u such that u is the solution of this inequality. So for those of you which are familiar, this is a variational inequality, a time-dependent variational inequalities, and we have a special operator S with some properties. We call it a history-dependent operator, and problem 2.1 is called a history-dependent variational inequality. Why we are studying such kind of mathematical objects? Because we have many, many examples arising in mechanics. Okay, so with this notation, we need, of course, some assumptions which guarantee the existence and uniqueness of the solution. Here you have the list of the assumptions. I do not present them in details, but let's just say that K is a non-empty closed convex subset of X, which is quite familiar, a popular assumption in convex analysis. Operator A is pseudo-monotone and strongly monotone, and you have the definition here. And operator S is a so-called history-dependent operator. That means it satisfies condition 2-4. So such kind of operator are very, very familiar in analysis, for instance, the Volterra type operators, the integral operators, but also in mechanics, they are involved in constitutive law of various viscoelastic materials. Okay, and the function J, it depends on 3 arguments. It's convex and lower semi-continuous with respect to the third one. It satisfies condition B, which is a gross condition. You have the constant alpha J, which satisfies a smallness condition. MA, I recall, it's a constant which appears in point B. It's constant in the strong monotonicity of the operator A. And of course, the function f, it's a continuous function. Okay, so the first result, which is not so new, we obtained it some years ago, guarantees the existence and uniqueness of the solution, a function which is continuous from 0t with values in x. The proof was obtained using arguments of elliptic variation inequality combined with a fixed property of the operator S, and I shall give you very shortly the ideas of the proof, which is obtained in several steps. In the first steps, we fix the function eta. We denote by y eta the function defined by 2, 8, and we solve the problem 2, 9. So you can see the color y eta in any time t, it's known at this stage. And a classical result of quasi-variational inequality shows that this problem has a solution, and we can prove that it is continuous in time. Then we define the operator lambda by formula 210, which associate to any eta the solution u eta, and we prove that this operator is not really a contraction, but the power of this operator is a contraction in the space of continuous function. So here we use some estimates, and this shows that this operator has a unit fixed point. We denote it by eta star. And now if you write the inequality presented before for eta star, so this inequality 2,9, we conclude that this is a solution, and this proves the existence part. The uniqueness part of the theorem follows from the uniqueness of the fixed point of the operator lambda. Okay, now we have a problem, the variational inequality. This is only an example. As I already told you, we can change the problem. We can consider a fixed point problem or optimization problem. And we have an existence, a unique result of the solution. Let us move to a convergence criterion and also to some well-posed results. We need some additional assumptions. So we reinforce the assumptions on A. We assume that it's still nonlinear, but Lipschitz continues, so condition 3.1. And on the function J, we have condition 3.2. Okay, and we formulate the following statement. So given a sequence of continuous function, un, we consider the two statements. So S1, un converges to u in the space of continuous function. S2, so there exists epsilon n, a sequence which goes to 0, such that you have condition A and condition B. So they are in red. That means that we relax the assumption, think to the solution. The solution has to be in K. So un of t is not in K, but is in some sense asymptotically in K. That means the distance between un and K at any time moment goes to 0. And the solution, the real solution, satisfies the inequality without the term in red. We relax this condition. That means we enlarge this inequality. We add this extra term, which makes easier to verify the inequality. So these two conditions play a crucial role in the proof. That means they are necessary and sufficient conditions for the convergence. So let me continue. Theorem number 2, under the previous assumption plus 3.2, the statements S2 implies the statement S1. That means any time when these relaxed conditions A and B are satisfied, you have the convergence. This is a convergence result. But what is important is that the convergence is true if, in addition, 3.1 is satisfied. So this theorem proves a convergence criterion because we have necessary and sufficient conditions for the convergence. Of course, we need some additional assumptions. At this moment, we cannot do better. Even so, some partial results have been obtained in the meantime. Removing or relaxing this condition deserves to be studied in the future. And the proof is based in several steps. It's based on several estimates, a fixed point structure of problem P, monotonicity argument, Gromard argument, and so on. So the outline of the proof is based on this statement S3. That means let us consider this additional intermediate statement, S3, where lambda is the operator I previously defined it. And there are some lemmas which represent the main step of the proof. Lemma 1 is a boundless result. So under the condition listed there, you have a constant such that the bounds are satisfied. Lemma 2 says that S1 and S3 are equivalent, and lemma 3 says that under the additional assumption 3 do, S1 implies S3, and also the converse if, moreover, 3, 1 holds. So these are quite technical lemma. I do not want to give the details. There are some estimates, but we can use these lemmas in order to end the proof. I mean, first, if we assume 2, 2, 2, 7, and 3, 2, we use lemma 3 to have the implication passing by S3. We obtain that S2 implies S1. And if we have, in addition, 3, 1, so we use the converse part in lemma 3 in order to see the S1 implies S2. So we have the equivalence, which concludes the proofs. Okay, so that's good. You have the problem, we have the solution, and moreover, you have a convergence criterion. What does it mean? It means that we are able to describe all the sequences which converge to the solution. So then we can move to some particular question. You know, in many situations I saw some result under these assumptions, the penalty method converge. Okay, then this is a paper. And then other people came and said, we discretize and show that the discrete conditions, the discrete solution converge to the solution. Another paper which says that we perturb the data and we converge the solution. And many, many papers which are practically epsilon improvement of some results. So I decided to think like this. We provide the necessary sufficient conditions which guarantee the convergence, and then if we are able to describe every sequence which converges to the solution, all the results in the previous paper are only particular results, because we have the criterion and we apply the criterion. That's it. So let me show how the criterion can be obtained in a penalty method. So let's assume the normalized duality map denoted by J. This is a univalued operator because X is strictly convex, but this is not a restriction because the space being reflexive, we can renorm it and to make it strictly convex. Let us define the operator P by this formula. Consider a sequence of parameter lambda n going to 0, and consider the penalty problems. You see, the penalty problems are written here, problem Pn, and the difference with the original problem is that we do not have constraints, so the solution takes value in X, not in K, and we test with test functions V in X, not in K, but in revanche, we have this extra term, the penalty term, which is involved in inequality. So we have the problem Pn. And the result is the following. For each n, there exists a unique solution of problem Pm. This is quite standard because it's practically the same result. But what is more important, the solution Un of problem Pn converges to the solution of problem P. And for the point B, which is the main point of this theorem, we have only to check that conditions 3, 3, and B are satisfied. If the conditions are satisfied by the penalty, the solution of the penalty problems, automatically we have the convergence. So this is why I say this is a particular result of our general result. Okay, but this is not all. We can define well-Posnet results. So well-Posnet concepts for nonlinear problems are very common in analysis, seeing to the concept of Hadamard, Tikhonov, Levitin, Polyak, and so. So practically these concepts vary from author to author, from paper to paper, but most of them are based on two main ingredients: the existence and uniqueness of the solution of the problem, and the convergence to this solution of a special class of sequences, call it the approximative sequences. So you define a special class and you see that you prove that this approximative sequence converges to the solution. More this class is larger, better is the concept. Okay, and so let us apply this principle in the study of our problem. I define here two concepts: the T1 approximative sequence, which is inspired by Tikhonov, which says the following: sequence UN is T1 if it belongs to K, the constraint is satisfied, and the inequality is approximatively satisfied. That means you add this extra term. It's okay, this is an approximative sequence. Now, the second concept is the following: a T2 approximative sequence is a sequence which satisfies condition 3.3 before presented. That means you have the inequality, the constraint is satisfied with by relaxing it, and you have this extra term. So maybe we go back to condition 3.3, which is here you see that this is a condition. Okay, so there is nothing to prove here. We have only two definitions. But it's clear that any T1 approximative sequence is a T2, but the converse is not true. And you have here a very, very simple pedagogical example. Assume that the problem consists to find a real valued function, solution of this inequality. So this is an example, a particular example of our problem. The sequence UN presented here in 5.1, it's a T2 approximative sequence, but it's not a T1. It's T2. Some computation has to be done. It's not a T1 because UN is not in K, K being the segment 0.1. Okay, and I continue the definition. Problem P is said to be Ti well posed, I equal 1 or 2, if it has a unique solution and every Ti approximative sequence converges to the solution. Now, what does it mean, this definition? If SP represents all the sequence converging to the solution, STI, the sequence of Ti approximative sequence, this definition says that the problem is Ty well posed if and only if the inclusion STY, including SP, holds. Okay, these are only definitions. Which are the results? Number 1, so theorem 4, problem P is T1 well posed under the basic assumption of the data. If we add an assumption, supplementary assumption 3.2, problem P is also T well posed, and moreover, if 3.1 also holds, then ST2 equal SP. So the proof is based on a standard argument, but what is important here is point C, that we have the best concept of well posed for this problem under the assumption presented here. We obtain it, concept, we constructed a concept which uses the largest possible set of approximated sequences. Okay, so this is mentioned here in the remark. So this inclusion always holds. Example 1 says that the inclusion is not strict. Definition 2 shows that T2 well posedness implies T1, so this Levitin-Polyak is better than Tikhonov well posedness concept. And number 3 says that under the additional assumptions, among all the concepts which makes the inequality is well posedness, this T2 is the largest set of approximative sequences. So here you can recover Hadamard, well-Posnet, and any other approximative sequence used in the literature. Okay, so this is the theory. The theory is quite abstract, but we develop it here because we had good models, and we can apply this in some physical problems, some engineering problems. And I shall present you to finish a contact model. So consider an elastic body, omega, which is in contact on gamma 3 with an obstacle. The obstacle is a rigid obstacle. That means it does not allow penetration, but you have a thin layer of asperities or deformable material. This is quite reasonable from physical point of view, because real surfaces are not perfect surfaces. They have asperities, and when the surfaces are in contact, they are deforming. So we consider the layer of asperities of thickness G deformable. So we make some physical assumptions. Probably I shall skip them. So we assume the body is elastic, the process is quasi-static, the contact is frictionless, only for simplicity. But we have unilateral construct with memory effects. What does it mean is that if you are doing charge and discharge, so the process is influenced by the previous values in time. So to solve the problem is not so easy. We need a mathematical model. A mathematical model is a system of partial differential equations which describes a phenomenon. So I list here the mathematical model. For those which are familiar with such kind of problem, it's okay. If not, there are many ingredients which are introduced here. The constitutive laws, the equilibrium equations, the displacement traction condition, and this nonlinear condition 6-5, which have a special physical meaning. And what's new in our model is this F, which depends on the history of the process. So you have penetration into the foundation, and it influences the process. Okay, so here are the notations. We explain it here. G is the thickness, R plus the positive part, F is the ill limit, which describes the accumulated penetration. And what about this problem? We wrote a mathematical model which corresponds to this physical setting. We provide its variational analysis, which is an interesting result because it motivates abstract theory. We prove some convergence result. How we prove them? Well, if we are able to describe all the sequences convergent to the solution, we just have to pick some particular sequence and to show that this sequence satisfies the criterion, and to provide some numerical simulations which validate the convergence result. So we use a lot of notation. Probably I do not want to present them in detail. So what's important is the set of, we are working in the space V for the displacement with the set U, which satisfies the constraint. We have an operator A, which describes the elastic property of the material. S, it's the memory property of the contact, and some other notation. And using integral by parts, we prove that the solution of the problem is a solution of this variational inequality, which is a particular case of the history-dependent inequality we studied. So this problem has a unique solution with this regularity. So we have to prove theorem 1. We check all the assumptions, and that's it. We have a solution which we call weak solution to the problem. And now let's move to some convergence result. So we have G, which is the thickness of the layer of elastic material, and we perturb it to G1. And we consider a problem, PVN, which is obtained by using, instead of Gn. So the solution, the set U is replaced by Un. This is the difference which is presented in red color. And under the previous assumptions, this problem has a unique solution, and the solution converges to the original solution when Gn goes to G. And for this convergence result, we use various estimates to prove that the sequence UN is a T2 approximated sequence. And then we use theorem 2. The second result is a convergence with respect to the yield limit. So remember that the operator S is with the first term, but we perturb it with a red term, omega n integral, when omega n is a function, measurable bounded function. And we consider the problem, the perturbed problem, that means the problem with, which satisfies this inequality. The set U is the same, but this time we perturb it the history-dependent operator. And under the previous assumption, this problem has a solution, and moreover, if omega n goes to 0, then un goes to u. And what about the proof? So it's quite easy, because we have just to say that the sequence un is a T2 approximative sequence. So these results are applied to the model, and besides the mathematically interesting is this convergence result, they have an important mechanical interpretation, because they show that the small perturbation in the thickness G of the asperities layer and the yield limit give rise to small perturbation of the weak solution. And this is important for engineers. Why? Because usually such kind of function which describes a contact are obtained by measurements, and you can have error in the measurements. And it's good to know that if you make small errors in the measurement, you obtain a solution which is not far to the real solution. So it's a good result for the model. Now, we provided some simulation. Actually, this was the job of my colleague, Professor Michael Barboteux, in the University of Perpignan in France, south of France, next to the Mediterranean coast, and nice place that I recommend you. And so the simulation are for this kind of problem. You have the physical setting, and the problem was supposed to be two-dimensional. There are some ingredients in the numerical treatment of the problem. More precisely, he used augmented Lagrangian approach, piecewise linear approximation, trapezoidal rule for the history operator. You have here the geometries, the values for the Young modulus, Poisson ratio, and so. I remember that the memory effects are of this form. F0 is fixed, but we perturb it with omega p of t, which depends on the history of the penetration. And look what happens. So we consider the problem with a G which is very close to 0, 10 power minus 16. So practically there are no asperities, it's like 0. And we compute the solution from Gn, which is not 0, it's strictly positive. And you see this, sequence of deformed meshes, and for n0, 16, 32, and so, practically you have this expression for the deformed force. The arrows represent the opposite of the reaction, and practically for G128, which is close to 0, you have a solution with, it's like a contact with a rigid obstacle. That means it's no penetration inside the obstacle. Why? Because the layer is very small. There is no asperities, so you have contact with a rigid foundation. And if we compute the solution for a given space parameter h and space of time or time step k, so it turned out that the difference in an appropriate norm converge to 0. So the numerical simulation validate this convergence result. And then concerning the dependence on the hardening parameter, so we have similar results. We test it with some omega n, which goes to 0, and we have the convergence of the difference, and that's it. Okay, so I shall be done in 2 minutes. This is only some example in variational inequalities, also in mechanics, but we can extend them to the more complicated situation, numerical simulation, contact models with viscoelastic material. Remember that we used to be in elastic materials here, and also viscoplastic and so on. So here are some references. The first one is a paper written with Michael Barbotte, is a special issue in the honor of Professor Ciarlet, who accomplished it this year, 85 years, and so it's a tribute to him. We were invited to present a paper, and so we presented these results. And if you are more interested in such kind of problems, there is a quite recent book about well-positive nonlinear problems. So the first part is purely functional analysis, some new concepts, and with application to minimization problems, inclusion, optimal control, inequalities, variational inequality, hemi-variational inequalities. And the second part of the book is application in contact mechanics, because with this theory we can establish a link between various problems which have a different form, but the solution of many problems converge to the solution of the fixed problem when some parameters converge in some sense. And this was a deal to show that some models in mechanics, but also in analysis, have this nice feature. So thank you for your attention. Yeah. We need pseudo-monotonicity for the existence. So as far as I know, we cannot avoid this assumption. Okay, thanks for this question. We can prove well-positive results. We can prove convergence results, but they are not optimal. That means they are not convergence criterion. That means we have convergence, one implication, but the converse is not true. That means if the sequence satisfies, in my slide it was S2, then it converges. This is enough for the application, but it's not said that if it converges, then it satisfies this condition. So we do not have the converse of the affirmation, but part of the results still remain valid. Now, if you put this question, it deserves to be studied in the future. And as I said, we have another criterion with some different assumptions, but they are not so constructive. You know, the criterion we have here is quite constructive because, you know, when you write this inequality, it's clear that basically you can see what we change. So we relax the constraint and we relax the term. This is very good also for numerics and very, very, in some sense, suggestive. The other criterion is based on some iteration and it's not so constructive, but still we can obtain such kind of result. Thank you. Thank you.